Okay, so in numerical methods, curve fitting is something very, very important, especially those who do experimental results. So you gather data, and you want to fit a model to this data. And this data usually it has an x-axis and a y-axis. The x-axis, we call it the independent variable. Like, for example, a distance. You are measuring, let's say, a temperature versus distance. So distance is an independent variable, and the y-axis will be the temperature, which is the dependent variable. This is the variable of your interest. This is the variable you want to fit a mathematical model so that you can represent that instead of a scattered point. It will be like a mathematical formula, and we will see why we need to do that. So there are different ways to do that. Regression is one way. In regression, actually, we are trying to find a curve that minimize the error between the points and the curve. So you can see here, let me just have the pointer here. Okay, so if you can see here, these are the scattered point, and here is the line that goes through these points. So we want to have the best fit. In regression, I don't want to have a curve that goes through all points like this. This is not of my interest, like this, like this. No, that's not. This is not helpful for me to go through all the points like this. This will be like a bad curve. And in machine learning language, we call this is overfitting, because yes, you can fit a perfect model. You can have like 20ish, 30ish order of polynomial and fit all the points. But once you have a new point, the prediction of that point will be very, very bad. So this is why we don't like, when you have a scattered in the data like this, we don't like to have a curve that goes through all the points. Instead, we are trying to fit here a linear model that somehow, we'll see that today, minimize the error between the model, which is in the red line, and the points, which are in the blue dots. Sometimes we fit a nonlinear model. So this week, we will cover only the linear model. Today, we will cover how we derive the formula for the linear model. And on Thursday, we will solve a couple of questions about the linear model. Okay, and then next week we'll talk about the different types of nonlinear models. So if we have something like this, the x-axis is my independent variable, which is the size in feet square of houses at the city of Waterloo. And in the y-axis we have the prices. Okay, I wish the prices in Waterloo in this range actually, it is much, much more than that. Depends on the size of the house, we have a price. And the objective here, if you are, for example, a real estate broker, you want to fit a model so that if you have another house with a data that does not include it here, you want to predict that. Okay, so you want to fit using regression the best model for this data. So this one way, which is a linear model, trying to fit a linear model here that goes, you can see has somehow minimizes the error. This is the best line. Always there is one unique line that minimizes the error, but in some cases the error is huge. You can see here the error between the points and the model is huge. Maybe you want to fit a nonlinear model, which is not really much better for that. And the reason why, because only using the size of the house to predict the prices, that's not really the best or the only feature. Because there are some other features that dictate the price of the houses. Let's say, for example, the area. Here in Waterloo, you could have identical houses, but they are in different areas, then you have totally different prices. So there are some other features that are not included. And for your information, whoever is interested in machine learning, regression is the starting point. Anyone teaches machine learning, the first thing they start with is regression. So regression is a statistical tool, and it is the base for machine learning algorithms. Many machine learning algorithms, especially the regression ones, they use linear or non-linear model. Now, in this course, we will not go deep from the perspective of machine learning. However, we'll talk about it from the more of numerical methods, and we'll talk about only one independent variable. So we will not use multi-regression problems. This is another topic, advanced topic. That's not the interest of this course, and this might be taught in a more advanced machine learning course. Okay, so we'll start with linear regression. So here I have x1, y1, x2, y2. These are actual data, experimental data that are scattered, as you can see here. Okay, this is xi, yi at the ith point, and I fit here. Okay, there's a question here. It says here, for a given problem, how do we decide which model would be best to use, linear or linear? Okay, that's a good question. Now, in this course, I will tell you. In the course, I will tell you which model to use. Now, I will tell you in the quiz and in the assignment. Now, you will see later on in the model, in the simulation assignment, you will be generating different models, and there is a criteria will tell you which one is the best. So even linear or nonlinear, there are many nonlinear models. There is a polynomial nonlinear, there is the exponential, etc. So which one is the best to fit the data? Usually we don't know in advance. Okay, so we have first to fit the model and then find the criteria that tells me how good or how bad is this model, and then based on this criteria I will see which one is the best. Okay, so for the sake of the assignments, you will see me clearly specify use a linear model, use an exponential model. In the exam, exactly the same thing I will do. I will specify the model, but in the simulation assignment, no, I will leave it for you to tell us which is the best model. Okay, so we have here the points are scattered all over the place, and then I came up with the best fit. This is my best fit, which I don't know yet how I will get this. So it's y equal to a0 plus a1x. So obviously we have two unknowns. The a0, which is the crossing with the y-axis, and the a1, which is the slope of the line. So I don't know which one that best fit this data, because as we said, you will not be going through all the points, but you want to minimize the error, which is, you can see it, this is the error between this point and the line. So I want to minimize. So is minimizing the error simply the error, meaning I will calculate the distance between the point and the line. Okay, see the error, and then sum all these errors, and the line that gives me the least error is the best line. Okay, so this is a good criteria or not? Let's see. So assume that I have these 4 points. So we have x and y. So x at 2 it's 4, and at 2 also it is at 3 it is 6, at 2 is 6, and at 3 it's 8. So very simple model. I have 4 points, and I want to fit a model based on the criteria, which is the summation of the error, which is the distance between my fit line and these points is minimized. Now, when we say minimize, it means that there should be only one unique solution. There should not be multiple solutions with this criteria. So let's move on. So the first line I came up with is this one, a line that goes through 2 points and misses the other 2 points. Okay, so the error between the line and this point is 0 because it's going through the point, but I have error here and an error there. So let's see here. This is the error 0 here between these 2 points, which is these 2. Now the error here is -2. And the error here is +2. So when we add all the errors, I will get 0. I mean, this is the best. The best is to get a zero error. I mean, this is not, but it doesn't look good for me actually. Having this curve, it looks to me like a very bad fitting curve. Yet I have a zero error. So, okay, let's see something else. Okay, I will, instead of fitting these 2 points, I will fit the other 2 points. Again, I will have an error here and zero error in the other point. So if you do the same thing, so now these 2 points become the ones that with the zero error, this one and this one. But again, I have the same problem. I have -2 and 2, and again 0. So I have 2 curves that they don't like good, and they are getting a 0 number, but yet it is this is really bad. I have an interesting question here. It says, how about the sum of the absolute error equal to 0? Okay, that's an interesting question for 2 aspects. The first one, because this is the coming slide. The second aspect, if I ask you, when the sum of the absolute error will be equal to 0, what is the condition that you will have? Instead of summing the errors, you are summing the absolute errors. At what condition you will have this summation equal to 0? Can I have a curve when all the errors, exactly, when all the errors, this is the answer, when all the errors equal to 0, meaning if my line that goes through all the points, remember in regression, the points are actually scattered. So there is no way I can have a linear model that fits all of them. If I have a linear model that fits all of them, I mean, this has become a trivial problem. Like a curve that has all the points on top of it, that's not really a numerical method problem. This is like it becomes a very simple high school or even less than high school problem. Okay, so the point here that I have scattered points, so there is no way I can have a linear model that fits all of them. So there is no way that the absolute error will be equal to 0 at any conditions in any practical numerical problem. But let's see what is what we will get. Okay, so here, as I said here, the sum of the residuals is minimized. However, we don't have a unique answer, and it's clearly that's not the best solution. Now, let's, as your colleague suggested, let's start to see what will happen if I make the absolute error equal to 0, and I will use the same points, and I will use the same curves as a matter of fact. And now here, instead of having -2 and 2, we will have 2 and 2. Okay, so the absolute error becomes equal to 4. And here, the absolute error is also equal to 4. Okay, so I have 2 curves. Both of them, they are giving me the same error. So that's not a unique solution. Which is, and how I can come up with this? This is no way I can find the best curve for this. So that's not really the best criteria. Now we come up here to the what we call the least square criteria, and this is the criteria we use. So the least square criteria minimizes the sum of the square of the residuals of the model. Okay. So here, this is my model, and here is my data point. Okay. Okay. So these are my data points. This is my data point, and this is my curve. So instead of minimizing the absolute value or minimizing the actual error, we will try to minimize the square of the error. Okay. Now, if I want to minimize the square of the error, it becomes an optimization problem. So if I can take the partial derivative of the residual of the error SR with respect to A0 and equate this to 0, and take the partial derivative of the same function with respect to the other variable, which is A1, and equate that to 0. So when I do this, I will have 2 simultaneous equations. I will solve for A0 and A1 because this is what I want to find, and then I will get a function that minimizes the square of the error. And this is what we call the least square technique. It's a very popular technique that is used to fit curves called the least square criteria. So let's come here. So this is my error now. I wanna do the partial derivative, as I said, with respect to a0. So if I do that, if the derivation is here and in our mini box, there is no need to go through it in details, but I will explain it to you. So here, I will take the partial derivative with respect to a0. So the partial derivative of this 2 times this times the derivative inside the bracket, which is -1. Okay, so this -1 can be cancelled, and this 2 can be cancelled because this is equal to 0. Okay, now I will take a0, a1 xi to the other side. Okay, I will come to this later. Now let's do the other one, which is taking the partial derivative with respect to a1 now. I think there's a typo in the notes that you have. This has to be a1, not a0. Now again, it becomes 2 times what is inside the bracket times the derivative of inside the bracket with respect to a1, which becomes -xi. Okay. So again, the minus sign and the 2 can be taken out. So now we will have these two formulas. The first formula is derived from here. Okay, so I have the summation of from I1 to n of a0, which is this term, take it to the other side, plus summation of I equal to 1 a1 xi, take it to the other side, and this is equal to the summation of yi. Now what do we know here? We know the xi's and sorry, the yi's and the xi's. What we don't know is these two constants. No, I can't. These are actually constant, so I can take this outside and I take this outside the summation because it's a constant. Now, if I take this outside the summation, what is the summation of I from 1 to n? Becomes an n. So this is n a of 0. This equation. The other equation becomes a1 summation of x of I goes from 1 to n equal to the summation of yi. Again, what are my unknowns? a0 and a1. So I have here one equation, but we have two unknowns. I cannot solve this with two unknowns. I need another equation, which is coming from this equation. So we'll come here. So this equation now, I will keep multiply xi times yi. This is in one side. In the other side, it becomes summation of a0 xi, which is this. The other one is summation of a1 x of I squared, because x of I times xi, which is this one. I will take the constant outside, so a0 outside, summation of x of I, and a1 is equal to take it out. And so these are two equations I have, and these two equations I can easily solve for them. Remember, this, and this, and this, and this, and this will be numbers. All these will be numbers. For example, here when I say summation of I goes from 1 to n of x of I. If x of I, let's say 1, 2, 3, 4, this is your x of I, this is x of I, and this is your y of I. This is, let's say, 2, 5, 7, and 10. Okay, so how we can apply this? This is goes from I goes to from 1 to 4. Okay, so then you add these values of x of I. So this becomes 1 plus 2 plus 3 plus 4, which is equal to 10. Same thing, summation of yi. You just add these numbers. So these becomes actually numbers. All of these becomes numbers. So I will have a 2 by 2 system of equations. Then I can solve for a0 and for a1. Very straightforward. Now I derived the formula for you in the final format for what will be your a0 and what will be your a1. So this will be your a1. Again, you don't need to know the derivation of that, although you can derive it yourself. It's not very difficult one. Okay, so here this is your a1 and here is your a0. So a1 is equal to this. Now everything here is a number. Okay, so this is a number, this is a number, a number, and a number. So this is, you can find A1, and then so first you find A1, and then you find A0. A0 is equal to this, or it is the average value of Y times A1, the average value of X. Okay. Then once you know A1 and A0, then you can find your model, which is A0 plus A1X. This is what you want to find, and this is what you were missing. Now, again, just to remind you, when we are in high school, we have a point that fits that exactly this, so we know actually the line fits all of them. There is no error here, so we are not concerned about the error. The only thing we need to find is the A0 and A1 here. Now here, I will have the point scattered. It's not. So I could have this curve, this curve, this curve, this curve. So I have an infinite number of lines that go through this one. Which one is the best? The one that satisfies this criteria. Okay, so this is what we call the least square criteria. Let me see if there is any question here. Yes, so we use the sum of the squared errors. This is the criteria, and this is why we call it the least square technique. Again, you don't need to memorize any of these formulas, okay? Because again, as you know, the quiz is open book, so you can just use it as it is. Next class, we'll see how we will use this formula. Okay, this is the last slide we will have today, or this is the last thing that we cover today. Okay, now I want to come up with a number criteria to tell me how good or how bad is my curve. Okay, so this is something very, very, very important that I'd like to know. Okay, okay. So here is I will define the term called S of t. Which is the sum of the squares around the mean of the dependent variables. So I have the dependent variable back here. Let me just remind you, this is your x of I, this is your y. Imagine that you are measuring temperature, okay, in x-axis. So this is, let's say, 1 meter, 2 meter, 3 meter, 4 meter. So this is 25 degree, 27, 28, 20, or 30, okay? So we are measuring temperature. So this is your dependent variable, so it has an average. There is an average value here. You try to find the average of these values, which is like maybe around 27 or 20, yeah, maybe around 27, 27.5, something like that. Okay, so this is, so here you take all your values that comes from your model, and you try to subtract that from this. From the average of your dependent variables, okay? And then we have the square of the error, which is SR. So we have ST and SR. So we will define the term called R square. R square is equal to ST minus S of R divided by S of T. Now, if of S of R, which is the error, is equal to 0, it means R square is equal to 1, and this is the best fit that you can ever have. If S of T and S of R are exactly the same thing, it means that this is really, really bad. The curve fit this is called coefficient of determination, and R is the correlation coefficient. So here we have no improvement when the R equal to R squared and equal to 1. It means that your error in the model and your average is exactly the same, which is a bad thing. It's a very bad fit when the error and your data are the average in the error and the actual data is the same, means it's really, really bad. Now this is where I will stop, but before I want to show you something here in Excel. Here is one question here. I don't. The residual is actually the difference in the error. Residuals means an error. It's a difference between your model and your data. This is what does it mean. Let me show you one thing here. Maybe you have done that a lot before, but you did not realize what was it. So let me open Excel. I want to show you something, and we'll be using this later on. Okay, so let me here. Let me do this. I will have an x axis and y axis. So this is like, as I said, 1 meter, 2 meter, 3 meter, 4, 5 meter. This is my dependent independent variable. I'm measuring temperature. So this is 25, 26, 27, 30, and 32, something like this. Okay. So I will draw this one here. I'm quite sure you have done this a certain time. So this is the points. Now I'd like to fit a linear curve here. So I will come here and I will set add trend line. Now here, this is the linear, okay? And here I want to display the equation and display the r squared. Okay, so if you look here, let me just increase the size here to see it so that you can see it. Okay, so this is the equation. Now, as you can see here, there is an error. The line does not go through all the points. There is an error here, a little bit there. Okay, let me make it more interesting here. Let me put this as 23. Okay, and let me put this one as 35. Okay, so there is, you can see an error here, and every time the curve is changing. Now, this is the least square technique. Okay, and there are other functions. We will try to see how we can find them, and you will see in the examples later on, I'm comparing the answer we derived with the Excel sheet. Okay, so here this is the A1 and this is the A0. It's calculated for you, and here is the R square 0.9469, which is like almost a perfect. As the line becomes better and better fit, this will become reduced. You see now it becomes 0.9837. Okay, if I make this is like 25, maybe I'll have even better. Okay, so you see 0.994. Now, if the line fits all the points, this becomes equal to 1. So this is an indication that you have, this is the best curve. And back to the first question I was asked, if the data is linear, it's clear, linear. You have only one model that best fit this. But if the data is non-linear, you will have many different types of models. There is a polynomial, there is an exponential, there are many other models. Which one to select? Because we don't know in advance which one is the best. So what you will be doing, and that will be doing in the simulation assignment, you will run all of them and you will calculate for each one the R squared. And the one with the highest R squared, this will be your this will be your best fit for the data.